Dear children, in the last classes we were seeing about the interference. In the last video we saw about the conditions for constructive and destructive interference. We know that whenever you have brightness, the path difference must be an integral multiple of lambda, or the phase difference must be an integral multiple of 2 pi. For darkness, the path difference must be an odd integral multiple of lambda, and the phase difference must be an odd integral multiple of pi. Now, this interference pattern was first observed by a scientist named Young, and it is called as Young's double slit experiment. So, we are using two slits over here which forms the two coherent sources. So, S1 and S2 are the two coherent sources which is derived from S. S is a monochromatic source of light which emits light waves continuously. So the light coming from S1 and S2 will have the same speed, same wavelength, same frequency, same amplitude, and they can either be in phase or have a constant phase difference. Now a screen is placed over here at a distance capital D from the double slit. The two sources must be very close to each other, and the distance between the two coherent sources or the two slits is represented by small d. Now let us calculate what is the path difference calculate the path difference between the two waves that is coming from S1 and S2. If you consider the point O, it is equidistant from S1 and S2. So all the wavelets will arrive at the point O in phase. Therefore, the point O is of maximum intensity, and it is the center point over here in the screen. Now, let us consider any other point P which is at a distance y from O. So now the wavelet from S1 and S2, they do not travel the same path, which means there is a path difference between the wavelet coming from S1 and S2. That path difference is represented by x, and this is what we are going to calculate now. So from this figure, what is x equal to? Can you write x as S2p minus S1p? S2, see the figure, S2p minus S1p will be the path difference. Now let us find out what is, you consider this triangle S2p and you can name some point over here. If you consider this triangle over here, if you use Pythagoras theorem, you get S2p squared is equal to d squared plus y plus d by 2 the whole squared. Can you see? S2p squared will be this squared plus this squared. This is y and this is d by 2. So d squared plus y plus d by 2 the whole squared. Similarly, what is S1p squared? It will be d squared plus, what is this one? This is y. So you can write it as y minus d by 2 the whole squared. But what is x squared minus y squared? It is x plus y into x minus y. That's what I have written over here. S2p minus S1p into S2p plus S1p equal to, you just subtract these two. D squared will get cancelled, and when you calculate y plus d by 2 the whole squared minus y minus d by 2 the whole squared, when you simplify it, you get 2yd. Now we need what is the path difference. So I have brought this to the denominator. We are going to make a small assumption over here. Since the point P lies very close to O, in the interference pattern, the maxima, minima, everything are very close to each other. The distance between them is very, very small. So if you consider the point P to lie very close to O, then you can say that this S1p and S2p can be approximately equated to capital D. If you consider the point P to lie very closely to O, S1p will be similar to S2p, and what is that distance? It is capital D. So in that case, S2P plus S1P will be D plus D, that is 2D. And when you substitute it here, you get the expression for path difference. So what is the expression for path difference? X is equal to YD by D. So from this figure, using Young's double slit experiment, we calculated what is the path difference between the two wavelets that is coming from the two coherent sources. We have already studied the condition for path difference for a maxima as well as for a minima. Now for a maxima or for constructive interference, what is the expression for path difference? It is n lambda. So let us equate this path difference and this path difference. That is yd by d equal to n lambda or y equal to n lambda d by d. So what is y? Y gives the position of the maxima. What is n here? N can be 0, 1, 2, 3, etc. When n equal to 0, you get y to be equal to 0, which means this point O is of brightness point. When n equal to 0, at y equal to 0, which is the position y equal to 0 here. So at this point, what do you get? You get a maxima. So when n equal to 1, you get y1 is lambda d by d. Similarly, y2 is 2 lambda d by d. What is y3? 3 lambda d by d. All this gives the position of the maxima. Similarly, let us calculate the position of the minima. Now, this is the expression for path difference. What is the condition for a path difference for a minima? It is 2n plus 1 into lambda by 2. It's where n is 0, 1, 2, 3, etc. You can also take it as 2n minus 1 into lambda by 2, where n is 1, 2, 3, etc. So in order to make our calculation easy, so I have, instead of taking 2n plus 1, I have written it as 2n minus 1. But you have to substitute n as 1, 2, 3, etc. This is because in the finding out the position of the maxima, I have written n equal to 0, 1, 2, 3. Here 0 corresponds to the center point. When n is equal to 1, you get the position of the first maxima and so on. Similarly, the center is already occupied by a maxima. So we needn't write for the value for n as 0. So in order to make the value for n equal to 1, I have used this equation. That is 2n minus 1 into lambda by 2. So in this expression, I found out what is y. This gives the position of the minima. You substitute n equal to 1, you get y is equal to lambda d by 2d. When n equal to 2, you get 3 lambda d by 2d and so on, which when n equal to 1, it gives the position of the first minima. When n equal to 2, it gives the position of the second minima and so on. Now, we have to find out. See, this is the interference pattern which we get on the screen over here. Now, this is a maxima. These are also called as interference fringes, interference band, or interference fringes they are called as. So the fringes is always represented in this manner. So if you see this figure, you can say that this is a maxima and this is a minima. This is again followed by a maxima, a minima, a maxima and so on. Now you have to calculate what is the distance between two consecutive maxima or the distance between two consecutive minima. So here how do you define this distance between two consecutive maxima is represented by the letter beta, where beta is called as the fringe width. Beta is called as the fringe width. So how do you define fringe width? Fringe width can be defined as the distance between two successive maxima or the distance between two successive minima. So the distance between two consecutive maxima will give the width of the dark fringe, and the distance between two consecutive minima will give you the width of the bright fringe. And we are going to calculate what is the width of the dark fringe and width of the bright fringe. So this is maxima. So the distance between two consecutive maxima will give you the width of the dark fringe. So let me take n equal to 1. When I take n equal to 1, y1 is so much. When I take n equal to 2, y2 is so much. So what is y2 minus y1? I get lambda d by d, which is represented by beta. Similarly, this beta is called the fringe width. Similarly, in this expression, substitute for y1 and y2. So what is y1? When you substitute n equal to 1, what is y1? You get lambda d by 2d. Substitute n equal to 2. So 4 minus 1, you get 3 lambda d by 2d. So what is y2 minus y1? It is equal to lambda d by d. So the width of the dark fringe is the same as the width of the bright fringe, and it is called as the fringe width, represented by beta. So using Young's double slit experiment, we have calculated what is fringe width by calculating what is the path difference.